Hello and welcome to Code Skwela. In this session, we are going to go through the Harvard CS50 Computer Science course. So right now we are in our second hour. So if you have happened to come across my uh, initial video or my first video prior to this one, uh, I have started a series of videos wherein I will go through the Harvard CS50 course. I will be doing it at 1 hour a day. So in a video, since the video is close to 25 hours, I'll be just uh, going through a 1 hour of it each day. Okay, so hopefully I'd be able to do or finish this or yeah, be able to do 1 hour a day for the next few days. Okay, and so yeah, uh, before we begin, I mean, so I have here my pen and my pen and my paper, just in case I need to take notes. And yeah, we have something to discuss also along the way as we uh, go through the course. And yeah, hopefully, this would be uh, another hour of fun and great learning for this course. So yeah, without further delay, let's continue and from where we left up from the last hour. And so yeah, come and join me and yeah, let's enjoy and uh, let's learn and enjoy. Okay, start.
Thank you. No, no -2 this time. So consider that even with this additional example, it still fits the same mental model, but in a little more interesting way. Here's that new function, ask something and wait. And notice that in this case, too, there's an input, otherwise known henceforth as an argument or a parameter, programming speak for just an input in the context of a function.
Okay, before we move on, just a review. In this part, he is talking about their application, which is named Scratch. So it's like a I don't know if you can call it a game, but it's an application wherein you can do some sort of coding, but in a visual way. Or yeah, so that's what he's showing us right now. And if you can review my first video, that at the end of it, the Scratch application is being discussed. Okay, this one is now a continuation of that, right?
And if we use our drawing as before to represent this thing here, we'll see that the input now is going to be, quote unquote, what's your name? The algorithm is going to be implemented by way of this new puzzle piece, the function called ask. And the output of that thing this time is not going to be the cat saying anything yet, but rather it's going to be the actual answer. So instead of the visual side effect of the speech bubble appearing, now nothing visible is happening yet thanks to this function. It's sort of handing me back like a scrap of paper with whatever I typed in written on it so I can reuse DAVID one or more times even like I did. Now what did I then do with that value? Well, consider that with the subsequent function, we had this say block 2 combined with a join. So we have this variable called answer. We're joining it with that first argument, hello. So already we see that some functions like join can take not one, but two arguments or inputs, and that's fine. The output of join is presumably going to be hello David or hello Carter or whatever the human typed in.
Okay, let's just pause for a minute here. Let me just double check my OBS if my microphone is, yeah, it's getting picked up. Sorry about that. Yeah, just quick interruption. Yeah, let's move on.
And that
Okay.
output, notice, is essentially becoming the input to another function, say, just because we've kind of stacked things or nested them on top of one another. But methodically, it's really the same idea. The input now are two things, hello, comma, and the return value from the previous ask function. The function now is going to be joined. The output is going to be hello David. But that hello David output is now going to become the input to another function, namely that first block called say. And that's then going to have the side effect of printing out hello David on the screen. So again, as sort of sophisticated as ours, as yours, as others' programs are going to get, they really do fit this very simple mental model of inputs and outputs. And you just have to learn to recognize the vocabulary and to know what kinds of puzzle pieces or concepts ultimately to apply. But you can ultimately really kind of spice these things up. Let me go back to my program here that just is using the speech bubble at the moment. Scratch, as an aside, has some pretty fancy interactive features too. I click the extensions button in the bottom left corner. And let me go ahead and choose the text-to-speech extension. This is using a cloud service. So if you have an internet connection, it can actually talk to the cloud or a third-party service. And
So with this one, with Scratch, I mean, with programming in general, you can think of the different parts of a program of like sort of like a Lego. You see, if you have played around with Legos, so Lego, its simplest, I mean, the most basic unit of a Lego is like a single block, right? You have a square where it has a button, sort of like a button on top, wherein that button is being used to attach itself to other set or to other Legos. Okay, so in that way you can connect several different Legos to form whatever uh, whatever figure you are trying to form. Okay, so yeah, in the same ways, programs are like that. It's composed of several different parts that you can put together to create more cohesive or full functioning program. Okay.
this one's going to give me a few new green puzzle pieces, namely the ability to speak something from my speakers instead of just saying it textually. So let me go ahead and drag this. And now notice I don't have to interlock them if I'm just kind of playing around and I want to move some things around. I just want to use this as like a canvas temporarily. Let me go ahead and steal the join from here, put it there. Let me throw away the say block by just moving it left and letting go. And now let me join this in. So
yeah.
I've now changed my program to be a little more interesting. So now let me stop the old version. Let me start the new. What's your name? Type in David, and voila.
Hello, banana.
OK, -2, for real. All right, so what I accidentally threw away there, intentionally for instructional purposes, was the actual answer that came back from the ask block. That's embarrassing. So now if I play this again, let's click the green icon. What's your name? David. And now,
Hello, David.
there we go. Hello, David. All right, thank you.
Nice. That's actually cool. Yeah.
OK, so
Simple
we have
enough.
these functions then in place. But what more can we do? Well, what about those conditionals and loops and other constructs? How can we bring these programs to life so it's not just clicking a button and voila, something's happening? Let's go ahead and make this now even more interactive. Let me go ahead and throw away most of these pieces. And let me just spice things up with some more audio under sound. I'm going to go to play sound meow until done. Here we go. Green flag. OK. It's a little loud, but it did exactly do what it said. Let's hear it again. OK, it's kind of an underwhelming program eventually, since you'd like to think that the cat would just meow on its own, but I have to keep hitting the button. Well, this seems like an opportunity for doing something again and again. So all right, well, if I wanted to meow, 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 let me just grab a few of these. Or you can even right-click or control-click, and you can copy-paste even in code here. Let me play this now. All right, so now like it's not really emoting happiness in quite the same way. It might be hungry or upset. So you know what, let's slow it down. Let me go to control, wait 1 second in between, which might be a little less worrisome. Here we go, play. OK, so if my goal was to make the cat meow 3 times, I dare say this code or algorithm is correct. But let's now critique its design. Is this well designed? And if not, why not? What are your thoughts here? Yeah. Yeah, sure. Yeah.
Yeah, because if
Yeah. So yeah, agreed. I could use
Yeah,
forever or repeat, but let me push a little
variable
harder. But why?
set of
Like this works.
repetitions,
I'm kind
then
of
yeah.
done with the assignment. What's bad
unless
about it?
it's very specific number of times that you
Yeah, there's
repeat
too
the
much
same
repetition,
thing.
right? If
Yeah.
I wanted to change the sound that the cat is making to like a different variant of meow or have it bark instead like a dog, I could change it from the drop down here apparently. But then I'd have to change it here, and then I'd have to change it here. And God, if this were even longer, that just gets tedious quickly. And you're probably increasing the probability that you're going to screw up and you're going to miss one of the drop downs or something stupid and introduce a bug. Or if you wanted to change the number of seconds you're waiting, you've got to change it in
Right.
2, maybe even more places.
More
Again,
places,
you're
yeah.
just creating risk for yourself and potential bugs in the program. So I do like the repeat or the forever idea so that I don't repeat myself. And indeed, what I alluded to being possible.
So yeah, this one, yeah, that could be the we can think of this concept as the idea of sort of like a best practice wherein it's called dry or don't repeat yourself. Yeah, if a same set of code does the same thing over and then it's spread all over your code base or in many places, it would be a good idea to isolate that one into a single function. Okay, so that if any changes are done uh, on that function, you don't have to change it uh, on some other places that it appears. Okay, or if that same logic appears, so you only have to change it in a single place. Okay. Oh, sorry.
Copy pasting earlier doesn't mean it's a good thing. And in code, generally speaking, when you start to copy and paste puzzle pieces or text next week, you're probably not doing something quite well. So let me go ahead and throw away most of these to get rid of the duplication, keeping just 2 of the blocks that I care about. Let me grab the repeat block for now. Let me move this inside of the repeat block. It's going to
Yeah.
grow to fit it. Let me reconnect all this and change the 10 just to a 3. And now play.
So you want to be a software engineer at Google? Go to algoexpert.io. Pick a question. Read the prompt.
Skip ads and continue.
So better. It's the same thing. It's still correct. But now I've set the stage to let the cat meow,
Yeah.
for instance,
It's more
4
compact
times by
and, yeah,
changing one thing,
it's more
40
flexible.
times by changing one thing. Or I could just use the forever block and just walk away, and it will meow forever instead. If that's your goal, that would be better. A better design, but still correct. But you know what? Now that I have a program that's designed to have a cat meow, wow, like why? I mean, MIT invented Scratch. Scratch is a cat. Why is there no puzzle piece called meow? This feels like a missed opportunity. Now, to be fair, they gave us all the building blocks with which we could implement that idea. But a principle of programming and really computer science is to leverage what we're going to now start calling abstraction. We have step-by-step instructions here, the repeat, the play, and the wait, that collectively implements this idea that we humans would call meowing. Wouldn't it be nice to abstract away those several puzzle pieces into just one that literally just says what it does, meow? Well, here's where we can make our own blocks. Let me go over here to Scratch under the pink block category here. And let me click Make a Block. And here I see a slightly different interface where I can choose a name for it. And I'm going to call it meow. And I'm going to keep it simple. That's it. No inputs to meow yet. I'm just going to click OK. Now, just going to clean this up a bit here. Let me drag and drop play sound and wait over here. And you know what? I'm just going to drag this way down here, because now that I'm done implementing meow, I'm going to literally abstract it away, sort of out of sight, out of mind, because now, notice at top left, there is a new pink puzzle piece called meow. And so at this point, I'd argue, it doesn't really matter how meow is implemented. Frankly, I don't know how ask or say was implemented by MIT. They abstracted those things away for us. Now I have a brand new puzzle piece that just says what it is. And this is now still correct, but arguably better design. Why? Because it's just more readable to me, to you. It's more maintainable when you look at your code a year from now for the first time, because you're sort of fondly looking back at the very first program you wrote. It says what it does. The function itself has semantics, which conveys what's going on. If you really care about how meow is implemented, you could scroll down and start to tinker with the underlying implementation details. But otherwise, you don't need to care anymore.
Yeah, so he was talking about abstraction. So in if in programming there's this concept of abstraction, right? Or especially most common in object-oriented programming, wherein you abstract away the functionalities of a certain let's say a class. If you use that within your code, you have no idea how it's being implemented. All you know is that it allows you to use this kind of function. Okay, so without worrying about how it's being implemented on its actual code. Okay, so in this case, yeah, the meow has been abstracted away into in its own function or method or in its own place, right? So you don't have to worry about the implementation details of that. You only have to worry about its output, okay, or what, or it is in, or its input, what it needs for it to execute correctly. Okay.
Now, I feel like there's a even additional opportunity here for abstraction and to sort of factor out some of this functionality.
You can think of abstraction as a way of hiding, right? Hiding implementation or hiding the working details of your functions, okay, or your methods.
It's kind of lame that I have this repeat block that lets me call the meow function, so to speak, use the meow function 3 times. Wouldn't it be nice if I could just call the meow function, aka use the meow function, and pass it an input that tells the puzzle piece how many times I want it to meow? Well, let me go ahead and zoom out and scroll down. Let me right click or control click on the pink piece here and choose edit. Or I could just start from scratch, no pun intended, with a new one. And now here, rather than just give this thing a name meow, let me go ahead and add an input here. And I'm going to go ahead and type in, for instance, n for number of times to meow. And just to make this even more user-friendly and self-descriptive, I'm going to add a label, which has no functional impact. It's just an aesthetic. And I'm just going to say times, just to make it read more like English in this case, that tells me what the puzzle piece does. And now I'm going to click OK. And now I need to refine this a little bit. Let me go ahead and grab, under control, a repeat block. Let me move the play sound and wait into the repeat block. I don't want 10, and I also don't want 3 here. What I want now is this n that is my actual variable that Scratch is creating for me that represents whatever input the human programmer provides. Notice it snaps right in place. Let me connect this. And now, voila, I have an even fancier version of meow that is parameterized. It takes input that affects its behavior accordingly. Now I'm going to scroll back up because out of sight, out of mind. I just care that meow exists. Now I can tighten up my code, so to speak, use even fewer lines to do the same thing by throwing away the repeat block, reconnecting this new puzzle piece here that takes an input like 3, and voila, now we're really programming. Right? We've not made any forward progress functionally. The thing just meows 3 times. But it's a better design. And as you program more and more, these are the kinds of instincts you'll start to acquire so that, one, you can start to take a big assignment, a big problem set, something for homework even, that feels kind of overwhelming at first, like, oh my god, where do I even begin? But if you start to identify what are the sub-problems of a bigger problem, then you can start making progress. And I do this to this day, where if I have to tackle some programming related project, it's so easy to like drag my feet or, oh, it's going to take forever to start, until I just start writing down like a to-do list. And I start to modularize the program and say, all right, well, what do I want this thing to do? Meowing. What's that mean? I got to have it say something on the screen. All right, I need to have it say something on the screen some number of times. Like literally a mental or written checklist, or pseudocode, if you will, in English on a piece of paper or text file. And then you can decide, OK, the first thing I need to do for homework to solve this real-world problem, I just need a meow function. I need to use a bunch of other code too, but I need to create a meow function. And boom, now you have a piece of the problem solved. Not unlike we did with the phone book there, but in this case, we'll have presumably other problems to solve.
So yeah, what he's saying is that for me, as in based on experience, when I code something, initially you code everything that you think would be necessary, but that code would initially be like messy and everything has been put in there without some thought. But eventually, as you refine your code, you'd end up with separating the different sections of it, that it would become more cohesive, right? So it would be much easier to read and understand. So that would be a common experience for me when I do code. So yeah, initially I'd start with a mess of a code, and then eventually, as I continue refining my code, I'd end up with several different functions of it. Okay, so the idea of divide and conquer is pretty much applicable when you are coding, okay, or when you are trying to program. So let's continue.
All right, so what more can we do? Let's add a few more pieces to the puzzle here. Let's actually interact with the cat now. Let me go ahead and now, when the green flag is clicked, let me go ahead and ask a question using an event here. Let me go ahead and say if, let's see, if the cursor, I want to do something like implement the notion of petting the cat. So if the cursor is touching the cat, like here, something like this. It'd be cute if like the cat meows, like you're petting a cat. So I'm going to ask the question when the green flag is clicked if, let's see, I think I need sensing. So if touching mouse pointer, this is way too big, but again, the shape is fine. So there it goes, grew to fill. And then if it's touching the mouse pointer, that is, if the cat to whom this script or this program, anytime I attach puzzle pieces, MIT calls them a script or like a program, if you will. Let me go ahead then and choose a sound and say play sound meow until done. All right, so here it is to be clear. When the green flag is clicked, ask the question, if the cat is touching the mouse pointer, then play sound meow. Here we go. Play. Huh. All right, let's try again. Play. Huh. I'm worried it's not Scratch's fault. Feels like mine. What's the bug here?
You have to click first.
Why doesn't this work?
Oh, yeah, the green flag is already there.
Yeah, who just turned? Yeah, the problem is the moment I click that green flag, Scratch asks the question, is the cat touching the mouse pointer? And obviously it's not, because the cursor was like up there a moment ago, and it's not down there. It's fine if I move the cursor down there, but too late. The program already asked the question. The answer was no, or false, or 0, however you want to think about it. So no sound was played. So what might the solution here be? I could move my cursor quickly, but that feels like never going to work out right. Other solutions here? Yeah, and way back? The forever loop. So I could indeed use this forever loop because if I want my program to just constantly listen to me, well, let's literally do something forever, or at least forever as long as the program is running until I explicitly hit stop. So let me grab that. Let me go to Control. Let me grab the forever block. Let me move the if inside of this forever block, reconnect this, go back up here, click the green flag, and now, nothing's happened yet, but let me try moving my cursor now. So now, that's kind of cute. So now the cat is actually responding, and it's going to keep doing this again and again. And so now we have this idea of taking these different ideas, these different puzzle pieces, assembling them into something more complicated. And I could definitely put a name to this. I could create a custom block. But for now, let's just consider what kind of more interactivity we can do. Let me go ahead and do this by, again, grabbing a when green flag clicked. Let me go ahead and click the video sensing. And I'm going to rotate the laptop because otherwise we're going to get a little inception thing here where the camera is picking up the camera is up there. So I'm going to go reveal to you what's inside the lectern here while we rotate this. And now that we have a non-video backdrop, I'm going to say this. Instead of the green flag clicked, actually, I'm going to say when the video motion is greater than some arbitrary measurement of motion, I'm going to go ahead and play sound meow until done. And then I'm going to get out of the way. So here's the cat, and we'll put him on top of there. Just OK. All right, and here we go. So my hand is moving faster than 50 something or other, whatever the unit of measure is.
That's cool. Nice.
And thank you. So now we have an even more interactive version. But I think if I sort of slowly, right, it's completely creepy, but I'm not like exceeding the threshold until finally my hand moves as fast as that. And so here actually is an opportunity to show you something a former student did.
Cool.
Let me go ahead here and, OK, got to stop this. Let me go ahead and zoom out of this in just a moment. If someone would be comfortable coming up, not only masked, but also on camera on the internet, thought we'd play one of your former classmates' projects here up on stage. Would anyone like to volunteer here and be up on stage? Who's that? Yeah, come on down. What's your name? Sahar? All right, come on down. Let me get it set up for you here. Let me go ahead and full screen this here. So this is Whack-A-Mole by one of your former predecessors. It's going to use the camera focusing on your head, which we'll have to position inside of this rectangle. And have you ever played the Whack-A-Mole game at an arcade? OK, so for those who haven't, these little moles pop up, and with a very fuzzy hammer, you sort of hit down. You, though, if you don't mind, are going to use your head to do this virtually. So let's line up your head with this red rectangle, if you could. We'll do beginner.
This is you and the amount of money you have to invest. And this is a typical company listed in the stock market and its shares. Judging by the size, you're not likely.
All right, here we go. Sahar. Give it a moment. OK, come a little closer. And now hit the moles with your head.
Oh,
There we go. 1 point. 1 point.
that's actually cool. Nice.
Nice. 15 seconds to go. There we go. Oh, yep, 1 point. Nice. 6 seconds. There we go. Quick. All right. A round of applause for Sahar. Thank you.
That's cool. Wow. That's actually very cool.
So beyond having a little bit of fun here, the goal was to demonstrate that by using some fairly simple primitives, some basic building blocks, but assembling them in a fun way with some music, maybe some new costumes or artwork, you can really bring programs to life. But at the end of the day, the only puzzle pieces really involved were ones like the ones I just dragged and dropped, and a few more because there were clearly lots of moles. So the student probably created a few different sprites, not a single cat, but at least 4 different moles. They had like some kind of graphic on the screen that showed Sahar where to position her head. There was some kind of timer, maybe a variable that every second was counting down. So you can imagine taking what looks like a pretty impressive project at first glance and perhaps overwhelming to solve yourself. But just think about what are the basic building blocks and pluck off one piece of the puzzle, so to speak, at a time. And so indeed, if we rewind a little bit, let me go ahead here and introduce a program that I myself made back in graduate school when Scratch was first being developed by MIT. Let me go ahead and open here. Give me just 1 second. Something that I called back in the day Oscar time that looks a little something like this.
I don't know if you can hear my background noise. I'm sorry about that. Yeah, hopefully you could still hear me and the video.
Of implementing this and hearing this song for like 10 straight hours. But it's a good example to just consider, how was this program composed? How did I go about implementing it the first time around? And let me go ahead and open up some programs now that I wrote in advance, just so that we could see how these things are assembled. Honestly, the first thing I probably did was probably to do something a little like this. Here is just a version of the program where I set out to solve just one problem first, of planting a lamppost in the program, right? I kind of had a vision of what I wanted. You know, it evolved over time, certainly, but I knew I wanted trash to fall. I wanted a cute little Oscar the Grouch to pop out of the trash can and some other stuff. But wow, that's a lot to just tackle all at once. I'm going to start easy, download a picture of a lamppost, and then drag and drop it into the stage as a costume, and boom, that's version 1. It doesn't functionally do anything. I mean, literally, that's the code that I wrote to do this. All I did was use like the backdrops feature and drag and drop and move things around. But it got me to version 1 of my program. Then what might version 2 be? Well, I considered what piece of functionality, frankly, might be the easiest to pluck off next. And the trash can. That seems like a pretty core piece of functionality. It just needs to sit there most of the time. So the next thing I probably did was to open up, for instance, the trash can version here that looks a little something now like this. So this time I'll show you what's inside here. There is some code, but not much. Notice at bottom right, I changed the default cat to a picture of a trash can instead, but it's the same principle that I can control. And then over here, I added this code. When the green flag is clicked, switch the costume to something I arbitrarily called Oscar1. So I found a couple of different pictures of a trash can, one that looks closed, one that looks partly open, and eventually one that has Oscar coming out. And I just gave them different names. So I said switch to Oscar1, which is the closed one by default. Then forever do the following. If touching the mouse pointer, then switch the costume to Oscar2, else switch to Oscar1. That is to say, I just wanted to implement this idea of like the can opening and closing. Even if it's not exactly what I wanted ultimately, I just wanted to make some forward progress. So here, when I run this program, by clicking play, notice what happens. Nothing yet, but if I get closer to the trash can, it indeed pops open because it's forever listening for whether the sprite, the trash can in this case, is touching the mouse pointer. And that's it. That was version 2, if you will. And if I went in now and added the lamppost and composed the program together, now we're starting to make progress, right? Now it would look a little something more like the program I intended ultimately to create. What piece did I probably bite off after that? Well, I think what I did is I probably decided, let me implement one of the pieces of trash, not the shoe and the newspaper all at once. Let's just get one piece of trash working correctly first. And so let me go ahead and open this one.
So yeah,
And again,
one way of tackling a problem is like you can start with the simplest one, okay, and then from there on you can start. What's important is that you have to start somewhere, and so if you could pick something that is simple or easy to solve or implement, then you start with that one so that it gets the ball rolling, okay? Because if you you might end up with overthinking. So eventually you'll have analysis paralysis wherein you get stuck thinking too much of how you would solve or approach a problem. So yeah, it would help greatly if you'd start small and start with the simplest one or the easiest one that you can tackle. Okay.
and all these examples will be available on the course's website, so you can see all of these examples too. It's not terribly long. I just implemented it in advance so we could flip through kind of quickly. Here's what I did here. On the right-hand side, I turned my sprite into a piece of trash this time, instead of a cat, instead of a trash can. And I also created, with Carter's help, a second sprite, this one a floor. It's literally just a black line, because I just wanted initially to have some notion of a floor so I could detect if the trash is touching the floor. Now, without seeing the code yet, just hearing that description, why might I have wanted this second sprite and this black line for a floor with the trash intending to fall from the sky? What might I have been thinking? Like, what problem might I be trying to solve? Yeah?
My name is Jim Rickards. I'm a former advisor to the CIA, Department of Defense, and the White House. In a moment, you'll have...
Yeah, you don't want the first sprite to start at the top, go through, and then boom, like you completely lose it. Like that would not be a very useful thing, or it would seem to maybe eat up more and more of the computer's memory if the trash is just endlessly falling and I can't grab it. It might be a little traumatic if you try to get it and you can't pull it back out and you can't fix the program. And so I just wanted the thing to stop. So how might I have implemented this? Let's look at the code at left. Here I have a bit of randomness, like I proposed earlier, exists. There's this blue function called goToX, y that lets me move a sprite to any position, up, down, left, right. I picked a random x location, either here or over here, negative 240 to positive 240, and then a y value of 180, which is the top. And this just makes the game more interesting. It's kind of lame pretty quickly if the trash always falls from the same spot. Here's just a little bit of randomness, like most any game would have, that spices things up. And so now if I click the green flag, you'll see that it just falls. Nothing interesting is going to happen, but it does stop when it touches the black line, because notice what we did here. I'm forever asking the question, if the distance of the sprite, the trash, is to the floor is greater than 0, that's fine. Change the y location to by -3. So move it down 3 pixels, until the distance to the floor is not greater than 0. It is 0 or even negative, at which point it should just stop moving altogether. There's other ways we could have implemented this, but this felt like a nice clean way that logically just made it make sense. And OK, now I got some trash falling. I got a trash can that opens and closes. I have a lamp post. Now I'm, a good 3 steps into the program. We're making progress. If we consider 1 or 2 final pieces, something like the dragging of the trash, let me go ahead and open up this version too. Dragging the trash requires a different type of question. Let me zoom in here. Here's the piece of trash. I only need 1 sprite, no floor here, because I just want the human to move it up, down, left, right. And the human's not going to physically be able to move it outside of the world. And if we zoom in on this code, the way we've solved this is as follows. We're using that and conjunction that we glimpsed earlier, because when the green flag is clicked, we're forever asking this question, or really these questions, plural, if the mouse is down and the trash is touching the mouse pointer, that's equivalent logically to clicking on the trash. Go ahead and move the trash to the mouse pointer. So again, it takes this very familiar idea that you and I take for granted every day on Macs and PCs of clicking and dragging and dropping. How is that implemented? Well, Mac OS or Windows are probably asking a question. Oh, for every icon, is the mouse down and is the icon touching the mouse? If so, go to the location of the mouse forever while that mouse button is clicked down. So how does this work in reality now? Let me go ahead and click on the play. Nothing happens at first, but if I click on it, I can move it up, down, left, right. It doesn't move thereafter. So I now need to kind of combine this idea of dragging with falling. But I bet I could just start to use just one single program. Right now I'm using separate ones to show different ideas. But now that's another bite out of the problem. And if we do one last one, something like the scorekeeping is interesting. Because recall that every time we dragged a piece of trash into the can, Oscar popped out and told us the current score. So let me go ahead and find this one. Oscar variables. And let me zoom in on this one. And this one is longer because we combined all of these elements. So this is the kind of thing that if you looked at it first glance, like, I have no idea how I would have implemented this from nothing, from scratch, literally. But again, if you take your vision and componentize it into these smaller bite-sized problems, you can take these baby steps, so to speak, and then solve everything collectively. So what's new here is this bottom one. Forever do the following. If the trash is touching Oscar, the other sprite that we've now added to the program, change the score by 1. This is an orange. And indeed, if we poke around, we'll see that orange is a variable, like an x or a y, but with a better name. Changing it means to add 1, or if it's negative, subtract 1. And then go ahead and have the trash go to pick random. What is this all about? Well, let me show you what it's doing, and then we can infer backwards. Let me go ahead and hit play. All right, it's falling. I'm clicking and dragging it. I'm moving it over, and I'm letting go. All right, let me do it once more. Letting go. Let me stop. Why do I have this function at the end called go to x and y randomly? Like, what problem is this solving here? Yeah, in way back.
It will hide the trash out of the...
Yeah, exactly. Even though the human perceives this as like a lot of trash falling from the sky, it's actually the same piece of trash just kind of being magically moved back to the top as though it's a new one. And there, too, you have this idea of reusable code.
Right.
If you were constantly copying and pasting your pieces of trash and creating 20 pieces of trash, 30 pieces of trash, just because you want the game to have that many levels, probably doing something wrong. Reuse the code that you wrote, reuse the sprites that you wrote, and that would give you not just correctness, but also a better design. Well, let's take a look at one final set of building blocks that we can compose ultimately into something particularly interactive as follows. Let me go ahead and zoom out here, and let me propose that we implement something like some kind of maze-based game. And let me go ahead here. So I want to implement some maze-based game that looks at first glance like this. Let me hit play.
Cool.
It's not a very fun game yet, but here's a little Harvard shield, a couple of black lines, this time vertical instead of horizontal. But notice you can't quite see my hand here, but I'm using my arrow keys to go down, to go up, to go left, to go right. But if I keep going right, it's not going anywhere. And left, it eventually stops. So before we look at the code, how might this be working? What kinds of scripts, collections of puzzle pieces, might collectively help us implement this? What do you think? Perfect. Yeah, there's probably some question being asked if touching the black line, and it happens to be a couple of sprites, each of which is just literally a vertical black line. We're probably asking a question like, are you touching it? Or is the distance to it 0 or close to 0? And if so, we just ignore the up, down, left, or rather, we ignore the left or the right arrow at that point. So that works. But otherwise, if we're not touching a wall, what are we probably doing instead?
Moving.
Forever here.
Keeps
How is the
moving
movement
to
working,
that direction.
presumably? Yeah, and back? Or are you scratching? OK, sure. Let's go on. Sorry, say it a little louder.
So you want to learn how to code? Go to programmingexpert.io. Watch our introductory video right your first.
Exactly. It's continually, forever looking or listening for the arrow keys, up, down, left, right. And if the up arrow is pressed, we're probably changing the y by a positive value. If the down arrow is pressed, we're probably going down by y and left and right accordingly. So let's actually take a quick look. If I zoom out here and take a look at the code that implements this, there's a lot going on at first glance. But let's see. First of all, let me drag some stuff out of the way, because it's kind of overwhelming at first glance, especially if you, for instance, were poking around online as for problem set 0 just to get inspiration. Most projects out there are going to look overwhelming at first glance until you start to wrap your mind around what's going on. But in this case, we've implemented some abstractions from the get-go to sort of explain to ourselves and to anyone else looking at the code what's going on. This is that program with the 2 black lines and the Harvard shield going up, down, left, and right. It initially puts the shield in the middle, 0, 0. It then forever listens for keyboard, as I think you were describing. And it feels for the walls, as I think you were describing. Now, how is that implemented? Don't know yet. These are custom blocks we created as abstractions to kind of hide those implementation details. Because honestly, that's all I need to know right now. But as aspiring programmers, if we're curious now, let's scroll down to the actual implementation of listening for keyboard. This is the one on the left. And it is a little long, but it's a lot of similar structure. We're doing the following. If the up arrow is pressed, then change by y by 1, go up. If the down arrow is pressed, then change y by -1, go down. Right arrow, left arrow, and that's it. So it just assembles all of those ideas, combines it into one new block, just because it's kind of overwhelming. Let's just implement it once and tuck it away. And if we scroll now over to the feel for walls function, this now is asking the question, as hypothesized, if I'm touching the left wall, change my x value by 1, sort of move away from it a little bit. If I'm touching the right wall, then move x by -1 to move a little bit away from it. So it kind of bounces off the wall. Just in case it slightly went over, we keep the crest within those 2 walls. All right, so then a couple of more pieces here to introduce. What if we want to actually add some kind of adversary or opponent to this game? Well, let me go ahead to maybe this one here, where the adversary in this game might, for instance, be designed to be bouncing, to stand in your way. If this is like a maze and you're trying to get the Harvard shield from the bottom to the top or vice versa, uh-oh, Yale is in the way, and it seems to be automatically bouncing back and forth here. Well, let me ask someone else. Hypothesize. How is this working? This is an idea you have. This is an idea you see. Let's reverse engineer in your head how it works.
So it's forever moving.
How might this be working?
Yeah, instead of forever, you move left and right until you hit the wall, depending on what side it is hitting, and then move to the opposite direction.
So if the Yale symbol is touching the left wall or the right wall, we somehow have it bounce. And indeed, we'll see there's a puzzle piece that can do exactly that, technically off the edge, as we'll see. But there's another way we can do this. And let's look at the code. The way we ourselves can implement exactly that idea bounce is just with a little bit of logic. So here's what this version of the program's doing. It's moving Yale by default to 0, 0, just to arbitrarily put it somewhere, pointing it direction 90 degrees, which means just horizontally, essentially. And then it's forever doing this. If touching the left wall or touching the right wall, here's our translation of bounce. We're just turning 180 degrees. And the nice thing about that is we don't have to worry if we're going from right to left or left to right. 180 degrees is going to work on both of the walls. And that's it. After we do that, we just move one step, 1 pixel at a time, but we're doing it forever, so something is happening continually. And the Yale icon is bouncing back and forth. Well, one final piece here. What if now we want a more another adversary, a more advanced adversary down the road, for instance, to go and follow us wherever we are, such that this time we want the other sprite to not just bounce back and forth, but literally follow us no matter where we go. How might this be implemented?
Okay, let's just pause. I'm gonna take a bathroom break. Hold on. Yeah, sorry about that. I just had a coffee like an hour ago, so yeah. All right, let's continue. Oops.
On the screen. I bet it's another forever block, but what's inside?
This one is cool. Yeah.
Yeah, forever
nice.
point at the location of the Harvard shield and go one step toward it. This is just going to go on forever. If I just give up, at least in this version, notice it's sort of twitching back and forth because it goes 1 pixel, then 1 pixel, then 1 pixel. It's sort of in a frantic state here. We haven't finished the game yet, but if we see inside, we'll see exactly that. It didn't take much to implement this simple idea. Go to a random position, just to make it kind of fair initially, then forever point towards Harvard, which is what we called the Harvard crest spray, move 1 step. Suppose we now wanted to make a more advanced level. What's a minor change I could logically make to this code just to make MIT even better at this? All right, change the number of steps to 2. So let's try that. So now they got twice as fast. Let me go ahead and just get this out of the way. Oops, let me make it a fair fight. Green flag. All right, I unfortunately am still moving 1 pixel at a time, so this isn't going to end well. It caught up to me. And if we're really aggressive and do something like 20 steps at a time, click the green flag. Jesus. OK, so that's how you might then make your levels progressively harder and harder. So it's not an accident that we chose these particular examples here involving these particular schools, because we have one more demonstration we thought we'd introduce today. If we could get one other volunteer to come up and play what was called by one of your predecessors Ivy's hardest game. Let's see, Hugh in the middle. Do you want to come on up? What's your name? Say again? Come a little closer, actually, and say it. Sorry, hard to hear here. All right, a round of applause here if we could too. OK, sorry, what was your name? Celeste. Celeste. Come on over. Nice to meet you, too. So here we have on this other screen Ivy's hardest game, written by a former CS50 student. I think you'll see that it combines these same principles. The maze is clearly a little more advanced. The goal at hand is to initially move the Harvard crest to the sprite all the way on the right so that you catch up to him in this case. But you'll see that there's different levels and different levels of sophistication. So if you're up for it, you can use just these arrow keys, up, down, left, right. You'll be controlling the Harvard sprite. And if we could raise the volume just a little bit, we'll make this our final example. There we go. Clicking the green flag. it for CS50. Welcome to the class. We'll see you next time.
Oh wow, we're done for that part. Okay, prior to moving on to the, I think that's another different lecture. So yeah, just to recap, yeah, for this, like for the past 45 minutes of this lecture, yeah, he's been talking about the different concepts that you mostly encounter when you are doing coding, or if you do get to work on projects, right, or in development projects. So, and basically things, the building blocks with functions is that it's just an input. The middle one is the, or the box, if you can recall the illustration, right, wherein he indicated the box as an algorithm or process, and then output. So just think of those three things that are the main components, right, of a function. So a function, it could or could not have an input, but it could also not have an output. But the main thing is the process that, or the things that are you'll be doing with those inputs, and also you'll be giving out the output as a result. Okay, so you've also mentioned abstraction. So abstraction is, you'll commonly encounter this, especially if you're doing object-oriented programming. But basically the idea is that uh, you are trying to encapsulate functionality or details of an implementation or a function in a separate, sort of like in a separate bubble. Think of it as bubbles, right? Inside a bubble, you don't know, or you can put that in a separate uh, bubble, and then yeah, you can mix and match and whatever, or combine those different bubbles to make a bigger bubble. Okay, which yeah would result in uh, whatever algorithm you are trying to accomplish. So one thing also is the idea of the divide and conquer. Okay, so breaking things down. So if you have a bigger task or a big problem to solve, so one good way of solving it is to breaking it down, right? So no matter how big a problem is, you can always break it down into smaller parts, which is much easier to work with than thinking of it as a whole, right? So one way also of dealing with problems is that do the simplest or the easiest problems. Okay, baby steps. Take the small steps first, so that it would allow you to start the ball rolling. Okay, because honestly, you cannot actually get solution in one sitting, or in one like in an immediately. Okay, you have to break it down and then analyze things that you could simplify, and then from there on you start doing the simplest thing that you can start, so as not to uh, let yourself fall into the analysis paralysis, wherein you get so stuck up with trying to solve the big problem, and you end up not doing or not starting at all. Okay, so that could be something that you might encounter later on if in your careers, if you start in software development or whatever. I guess it would also still applies to whatever endeavor that you will be doing. Okay, so yeah, I think that was quite a good session, I mean good lecture. And so yeah, we are now entering the new lecture, or this is probably a different one from the first one. But let's continue. We have right around 15 more minutes to complete our second hour, or R2 of this Harvard CS50 course. Okay. C. This is probably the programming language C.
Is it possible to become a data analyst without any experience in IT?
Yes.
Can a data analyst work as a
All right, so this is CS50, and this is week 1, the one in which you learn a new language, which is something we technically said last week, at least if you had never played with this graphical language known as Scratch before, which itself was a programming language. But today, as promised, we transition to something a little more traditional, a little more text-based, not puzzle piece or block-based, known as C. This is an older language. It's been around for decades, but it's a language that underlies so many of today's more modern languages, among them something called Python that we'll also come to in a few weeks' time. Indeed, at the end of this semester, the goal is for you to feel that you've not learned Scratch, you've not learned C, or even Python for that matter, but fundamentally that you've learned how to program. Unfortunately, when you learn how to program with a more traditional language like this, there's just so much distraction. Last week, I described all of the syntax, all of the weird punctuation that you see in this, like the hash symbol, these angled brackets, parentheses, curly braces, \n, and more. Well, today, we're not going to reveal what all of those little particulars mean, but by next week, will this no longer look like the proverbial Greek to you, a language that presumably you've never actually seen or typed before. But to do that, we'll explore some of the very same topics as last week. So recall that via Scratch and presumably via problem set 1, we took a look at things called functions that are actions or verbs. And related to functions were arguments like inputs. And related to some functions were return values like outputs. Then we talked a bit about
Arguments
conditionals,
or
forks in the road,
parameters.
so to speak, Boolean expressions, which are just yes/no questions or true/false questions, loops, which let you do things again and again,
Yeah, all of
variables,
these things are
like in math, that let you
constructs
store values temporarily, and then
of a
even
programming
other
language.
topics still.
Yeah.
So if you were comfortable on the heels of problem set 0 and last week, realize that all of these topics are going to remain with us. So really today is just about acquiring all the more of a mental model for how you translate those ideas into presumably a very cryptic new syntax. A new syntax, frankly, that's actually more simple in some ways than your own human language, be it English or something else, because there's far fewer vocabulary words. There's actually far less syntax that you might have in, say, a typical human language. But you need to be, with these computer languages, all the more precise so that you're most ultimately correct. And ultimately, we'll see, too, your code is successful along a few other lines as well. So if you think about like the last time you kind of wandered around not really knowing what you were doing or encountered something new, might not have been that long ago, entering Harvard Yard for the very first time or old campus or the like, be it in Cambridge or New Haven. You know, you didn't really need to know how to do everything as a first year. You didn't need to know who everyone was, where everything was, how Harvard or Yale or anything else for that matter worked. You sort of got by day to day by just focusing on those things that matter. And anything you didn't really understand, you sort of turn a blind eye to until it's important. And that's indeed what we're going to do today. And really for the next several weeks, we'll focus on details that are initially important and try to wave our hands, so to speak, at details that, yeah, eventually we'll get to, might be interesting, but for now they might be distractions. And by distractions, I really mean some of that syntax to which I alluded earlier. So by the end of today, and really by the end of problem set 1, your first foray presumably into this language called C, you'll have written some code. And you'll be asking yourself, we'll be asking yourselves, just how good is that code? Well, first and foremost, per last week, be it in Scratch or phone book form, like code ultimately needs to be correct to be well done, right? You want the problem to be solved correctly, so that one sort of goes without saying. And along the way, this term will provide you with tools and techniques, so you don't have to just sit there sort of endlessly trying an input, checking the output, trying another input, checking the output. There's a lot of automation tools in the real world and in this class and others like it that'll help facilitate you answering that question for yourself. Is my code correct according to our specifications or the like? But then something that's going to take more time, and you're probably not going to feel 100% comfortable with the first week, the first weeks, is just how well designed your code is. It's one thing to sort of speak English or write English, but it's another thing, or any language for that matter, but it's another thing to speak it or write it well. And we spent all these years in middle school, high school, presumably, writing papers and other documents, getting grades and feedback on them as to how well formulated your arguments were, how well structured your paper was, and the like. And there's that same idea in programming. It doesn't matter necessarily that you've just solved the program, a problem correctly. If your code is a complete visual mess, or if it's crazy long, it's going to be really hard for someone else to wrap their mind around what your code is doing, and indeed to be confident if it is correct. And honestly, you, the next morning, the next year, next time you look at that code, might have no idea what you yourself were even thinking. But you will if you focus too on designing good code, getting your algorithms efficient, getting your code nice and clean, and even making sure your code looks pretty, which would describe as a matter of style. So in the sort of written human world, having punctuation in the right place, capitalization and the like, the sort of way you write an essay, but not necessarily send a text message, relates to style, for instance. And so good style in code is going to have a few of these characteristics that are pretty easily taught and remembered, but you just have to start to get in the habit of writing code in a certain way. So these three axes, so to speak, correctness, design, and style, are really the overarching goals when writing code that ultimately is going to look like this. So this program we conjectured last week does what if you run it on a Mac or PC or somewhere else, presumably?
It will display
What
the
does it do?
hello
Yeah.
world string on the screen.
It just prints hello world. And honestly, that's kind of atrocious that you need to hit your keyboard keys this many times with this cryptic syntax just to get a program to say hello
Yeah.
world. So a spoiler, in a few weeks' time when we introduce other more modern languages like Python, you can distill this same logic into literally one line of code. And so we're getting there ultimately, but it's helpful to understand what it is that's going on here, because even though this is a pretty cryptic syntax, there's nothing after this week and really next week that you shouldn't be able to understand, even about something that right now looks a little something like this. So how do you write code? Well, I've given us sort of the answer to a problem. How do you print hello world on the screen? So what do I do with this code? Well, we're in the habit of typically writing things with like Microsoft Word or Google Documents. And yeah, I could open up Word or Google Docs or Pages or the like and just literally transcribe that character for character, save it, and boom, I've got a program. But the problem, per last week, is that computers only understand or speak what other language, so to speak?
First, we have Grammarly. The free version checks basic spelling and grammar. Grammarly Premium, on the other hand,
Yeah, so binary, zeros and ones. And so this obviously is not zeros and ones. So it doesn't matter if I put it in a Word doc, Google Doc, Pages file, or the like. The computer's not going to understand it until I somehow translate it to zeros and ones. And honestly, none of those tools that I rattled off are really appropriate for programming. Why? Well, they come with features like boldfacing and italics and sort of fluffy aesthetic stuff that has no functional impact on what you're trying to do with your code. And they don't have the ability, it would seem, to convert that code ultimately to zeros and ones. But tools that do have this capability might be called integrated development environments, or IDEs, or more simply, text editors. A text editor is a tool that a programmer uses perhaps every day to write their code. And it's a simple program. Here, for instance, a very popular one called Visual Studio Code, or VS Code. And at the top here, you see that I've actually created in advance, before class, a very simple empty file called hello.c. Why? Well, .c indicates by convention that this is going to be a file in which there is C code. It's not .docx, which would mean in this file is a Microsoft Word document, or .pages is a Pages file. This is .c, which means in this file is going to be text in the language called C. This number 1 here is just sort of an automatic line number that's going to help me keep track of how long or short this program is. And the cursor is just blinking there, waiting for me to start typing some code. Well, let me go ahead and type out exactly the same code. For me, it comes pretty comfortably from memory, so I'm going to go ahead and include something called standardIO.h. More on that later. I'm going to sort of magically type int main void, whatever that means. We'll come back to that later. One of these curly braces, and then a sibling there that closes the same. Then I'm going to hit tab to indent a few spaces, and then I'm going to type not print, but printf,
coded in C.
then hello, comma, world, backslash n, close quote, close
line
parenthesis,
number 1 would be
semicolon. I
header
dare say
files
this was essentially the very first program I wrote some 25 years ago. I wrote it to say, hi, CS50. Now it just says the more canonical, conventional hello world. But that's it. That's my very first program. And all I need to now do is maybe hit Command S or Control S to save the file. And voila, I am a programmer. The catch, though, is, like, OK, how do I run this? Like on your Mac or PC, how do you run a program? Well, usually double-click an icon. On your phone, you tap an icon. In this environment that we're using, and that many programmers, dare say most programmers use, you don't have immediately a nice, pretty icon to double-click on. That's very user-friendly, but it's not very necessary, especially when you get more comfortable with programming. You're going to want to type commands, because it's just faster than pointing and clicking a mouse. And you're going to want to automate things, which is a lot easier if it's all command or text-based as opposed to mouse and muscular movements. And so here, I have my program. It lives in this file called hello.c. I need to now convert it, though, to zeros and ones. Well,
Compile
how
it.
do I go about doing this, and how am I going to get from those this so-called code or source code, as it's conventionally called, to this, these zeros and ones that we'll now start calling machine code. The zeros and ones from last week can be used not only to represent numbers and letters, colors, audio, video, and more. It can also represent instructions to a computer, like print, or play a sound, or delete a file, or save a file. All the sort of basics of a computer somehow can be represented by other patterns of zeros and ones. And just like last week, it depends on the context in which these numbers are stored. Sometimes they're interpreted as numbers, like in a spreadsheet. Sometimes they're interpreted as colors. Sometimes they're interpreted as instructions, commands to your computer to do very low-level operations like print something on the screen. So fortunately, like last week's definition of like computer science, of problem solving, is a nice mental model for exactly the goal at hand. I have some input, aka source code. I want to output ultimately machine code, those zeros and ones. I certainly don't want to do this kind of process by hand. So hopefully there's an algorithm implemented by some special program that does exactly that. And those of you who do have some prior experience, this program might be called a compiler. So a few of you have indeed programmed before. Not all languages use compilers. C, in fact, is a language that does use a compiler. And so I just need to find myself on my computer somewhere, presumably, a so-called compiler, a program whose purpose in life is to convert one language to another. And source code, written textually in C, like we saw a moment ago, is source code. The machine code is the corresponding zeros and ones. So let me go back to this same programming environment called Visual Studio Code, or VS Code. This is typically a program you or any programmer on the internet can download onto their own Mac or PC and be on their way with whatever computer you own writing some code. A downside, though, of that approach is that all of us have slightly different versions of Macs or PCs. We have slightly different versions of operating systems. They may or may not be up to date. It's just sort of a technical support nightmare to create a uniform environment, especially for like an introductory class where everyone should ideally be on the same page so we can get you up and running quickly. And so I'm actually using a cloud-based version of VS Code, something that you only need a browser to access, and then you can be on any computer today or tomorrow. By the end of the semester, we're going to get you out of the cloud, so to speak, as best we can, and get you onto your own Mac or PC so that after this class, especially if it's the only CS class you ever take, you feel like you can continue programming in any number of languages, even with CS50 behind you. But for now, wonderfully, the browser version of VS Code should pretty much be identical to what the eventual downloadable version of the same would be. And you'll see in problem set 1 how to access this and how to get going yourself with your first programs. But I haven't mentioned this bottom part of the screen, And this is an area where we have what's called a terminal window. So this is sort of old school technology that allows you, with a keyboard, to interact with a computer, wherever it may be, on your lap, in your pocket, or even, in this case, in the cloud. So on the top-hand portion of this screen is my text editor, like tabbed windows, like in many programs where I can just create files and write code. The bottom of the screen here, my so-called terminal window, gives me the ability to run commands on a server that currently I have exclusive access to. So because I logged into VS Code with my account online, I have my own sort of virtual server, if you will, in the cloud, otherwise known as, in this context, a container. This has its own operating system for me, its own hard drive, if you will, where I can save and create files of my own separate from yours and vice versa. And it's at this very simple prompt, which is conventionally, but not always, abbreviated by a $, has nothing to do with currency. It just means type your commands here. This is where I'm going to be able to type commands like compile my source code into machine code. So it's a command line interface, or CLI, on top of an operating system that you might not have ever used or seen, but it's very popular, called Linux. Odds are almost all of us in this room are using Mac OS or Windows right now. But we're all going to start using an operating system called Linux, which is in a family of operating systems that offer not only this command line interface, but are used not just for programming, but for serving websites and developing applications and the like. And it's indeed a familiar and very powerful interface, as we'll see. So how do I go about making this file, hello.c, into a program? There's no icon to double click, but there is a command. I can type make hello at this $ prompt, go ahead and hit enter, and nothing appears to happen. But that's a good thing. And as we'll see in programming, almost always, if you don't see anything go wrong, that means everything went right. So this is going to be a rarity at first, but this is a good thing that it just seems to do nothing. But now, there is in the folder in my account on the cloud a file called hello. And it's a bit of a weird command, but you'll get familiar with it before long. Dot just means go into my current folder. /hello means run the program called hello in this current folder. So /hello and then enter, and voila. Now I'm actually not just programming, but running my actual code. So what have I just done? Let me go ahead and do this. I'm going to go ahead and open up the sidebar of this program. And you'll see in problem set 1 how to do this. And this might look a little different based on your own configuration. Even the color scheme I'm using might ultimately look different from yours because it supports nice colorful themes. So you can have different colors and brightnesses depending on your mood or the time of day. What I've opened here, though, is what is called in VS Code Explorer. And this is just all of the files in my cloud account. And there's not many right now. There's only 2. One is the file called hello.c, and it's highlighted because I've got it open right there. And the other is a file called hello, which is brand new and was created when I ran that command.
Yeah, that's the
and what's now
program
worth noting
that
is
has
that
been
now things
generated
are getting a
after the
little more like
compilation.
Mac OS and Windows. Like on the left-hand side, you have a GUI, a graphical user interface. But on the bottom here, again, you have a CLI, command line interface. These are just different ways to interact with computers. And you'll get comfortable with both. And honestly, you're certainly familiar and comfortable with GUIs already. So it's the command line one with which we'll spend some time. Now, suppose that I just wanted to do something more than compile this program. Suppose I wanted to go ahead and remove it. Like, no, I made a mistake. I want to say hello CS50, not hello world. I could just hover up here like in any software, and I could right-click, and I could poke around, and there, delete permanently. So most of us might have that instinct on a Mac or PC. You right-click or control-click, and you poke around. But in a command line interface, let me do this instead. The command for removing or deleting a file in the world of Linux, this other operating system, is just to type rm for remove and then hello, enter. It's a somewhat cryptic confirmation message, but this just means, are you sure? I'm going to go ahead and type y for yes. And now when I hit enter, watch what happens at top left in the Explorer, the GUI, the graphical interface. Voila, it disappears. Right, not terribly exciting, but this just means this is a graphical version of what we're seeing here. And in fact, if you want to never use the GUI again, I'll go ahead and close it with a keyboard shortcut here. You can forever just type ls for list and hit enter. And you will see in the command line interface all of the files in your current folder. So anything you can do with a mouse, you can do with this command line interface. And indeed, we'll see many more things that you can do as well. But
Okay. So now an hour has passed, and yeah, we have completed our second hour of this Harvard CS50 course, computer science course. And yeah, so far it's been again a great experience. Yeah, a while ago I had a recap of what happened in lecture 0, wherein there was a presentation of the Scratch application wherein you can build or create programs visually. So with Scratch, it allows you to program something. Like in their examples, they are mostly games, wherein you can create games by doing the Scratch, doing it on the Scratch application, where you can just stack visual representations of code. And then, yeah, it was actually really cool that you are able to generate different things or create different games using just Scratch alone. So it allows you to understand the different concepts of a programming language, okay? Which would come in handy when you shift into a learning actual programming language or languages, okay? So now we have also started with in the next in its another lecture, which is lecture 1 in this, based on the timestamp here on this chapter. So now we are starting to learn about C. So C is a programming language that allows you to code and create programs with. So yeah, this one is, we have already started with the introduction. And so yeah, basically with C, most of, I guess, I don't know if everything or most of schools, universities, colleges would definitely start with C, or it's a common programming language that is being taught in schools. Okay, and so yeah, also a quick summary. C is a compiled programming language. So there are two types of programming languages as far as I know. There's a compiled one and there's an interpreted one. Okay, so there are several programming languages that are compiled, and then there are also interpreted. Okay, so we will not dig in deep into that, why it is compiled or interpreted. It's just a way of uh, building programs in two different ways. Okay, and then he has also introduced VS Code. So with VS Code, it's an IDE or integrated development environment, sort of like a software or a program or an application that you use to write your code. Okay, so with VS Code, it's from Microsoft, so it allows you to use, or you can code using VS Code with different programming languages. Okay, so with VS Code, it supports so many different programming languages. C is only one of them. Okay, and then also he introduced the terminal, or yeah, the command line interface, wherein you execute commands via this kind of interface, wherein you have only a prompt or a single line, and you type in the code or whatever commands that you want the computer to execute. Okay, that includes compiling and generating the actual program from your code. Okay, so which is what is a common way of uh, creating programs with C. Okay, that also includes like C++, C Sharp, Java, and yeah, and most other major programming languages. Okay, so I guess we'll see you again uh, on the next hour, in our uh, third hour, or in hour number 3. Hopefully tomorrow, or yeah, if things are well, then I should be able to uh, give that to you in the coming days. And so yeah, uh, again, please do not forget to hit the subscribe button or like this video if you like it. And yeah, and if tell me if you have your whatever thoughts and ideas that you have, let me know in the uh, comment section. And yeah, or you can ask also questions, and yeah, we'll try to answer it uh, if that is possible for me to answer. Okay, so just remember, I'm not an expert in all of these things. Yeah, but we will try. And so yeah, I guess that's the most of it. I'll see you again in our next session, and continue learning. And yeah, we'll see each other, and see you soon, and bye bye.